Hello everyone. Today we will be talking about a recent work, Deep MultiView Supervision for Surface Mapping Estimation. We will be going over the what, why, and how of the task. So let's dive straight into it. Let's first look at what we want to do. We have an image of a face and another image of a different face. If you notice closely, you'll see some color points on the faces. On even closer inspection, we see these points mapped to roughly the same semantic location in each of these faces: the eye, the mouth, and the chin. If we're able to do this for each of all the points in the images, we can perform dense correspondence between these pairs of faces. Let's look at some more examples. We again have multiple faces with the same colored points. However, we notice performing dense correspondence on them directly is tough due to varying perspectives and underlying shapes. So we can attempt to use the underlying 3D shape to make our lives a bit easier. However, although we've reduced some of the variance, this task still contains a lot of variables. The points we've labeled are universal across these instances, despite the different shapes, so ideally a universal representation for the same would be ideal. To solve this issue, we introduced the concept of a top-down mapping. That is, a semantic mapping between these points and their semantic meaning, which serves as a universal blueprint for the face category. Note that the different categories can have different top-down maps. So if you see the eye gets mapped to this, the chin gets mapped to the yellow point, the gray mouth gets mapped to this. And it's the same for all the images, despite the differences between them. Our task basically becomes given an image, predict where each point lies on top of this top-down map. Now that we know the basics, the next natural question is to ask how to teach a model to do this. How does the model learn how to do this? Most early approaches rely on dense supervision, where they label such information and serve that as a supervision for the network. However, there has been recent work by Kulkarni et al., which allows you to ignore this need for heavy supervision. However, it is still limited by fixed ratios. We propose our approach, which simultaneously learns to predict both the underlying shape and surface mapping, and also uses multiple views to improve performance. Let's move on to why would you want to do this. The simple reason being, creating such labels for new categories is a very tough task. The amount of labels required just makes this unfeasible to extend to new categories. Now let's move on to the contributions in this paper. We release a new dataset to allow research in this direction, and our approach, which demonstrates clear performance improvements, allowing us to reduce the need for supervision. So let's first take a look at the data set. We provide multiple faces in the real world, synthesize multiple views of the same, smoothly varying them. We also provide the respective 3D shapes. We also provide the same for categories such as cars and supplemental data such as depth, camera poses, surface normals, segmentation masks. And we similarly do the same for planes as well. And we hope that our dataset encourages research in this direction. Let's now move on to our approach and see how we tackle such a task. Let's look at a vanilla version of the model, predict both the top-down map and 3D shape from the same image. We would supervise it using the ground truth labels and train the individual heads to. So all of this looks good. However, we don't want to use such supervision anymore. We don't want such dense labels. So the question remains how to predict something without exactly knowing the value. Let's look at this step by step. Our approach consists of three main components: reprojection, deformation, and multiple consistency. Let's first take a look at one of our core components, which is the reprojection side. Assume we know the true top-down mapping. So you know how to go from the image to the top-down and the underlying 3D shape. So you know how to go from the top-down map to the 3D point in the board. So what happens is we can follow any dot, for example, the green dot, and we can go to the corresponding location in the top-down map. And here we can go to the corresponding 3D face. Once it reaches to 3D shape, if we know the camera pose used to generate this image, we can reproject this 3D point back to the original image. If everything goes correctly, if all our information was correct, we should be able to reach the exact same point where we started. And if we don't, then we can use this inconsistency as a form of supervision. If we revisit our model, we find that our two heads are basically the two steps in this cycle, one being image to top down and the other being top down to 3D. This basically means our network can be a part of the reprojection cycle and can help us complete this. Now let's take a look at how this comes together. We can replace our original ground truth losses, our original supervision, with the loss made using the inconsistency in the reprojection segment. And that's how we perform learning without the need for ambiguities. However, although this sounds good, we notice training with both the heads simultaneously in such a loosely supervised setting is very tough. So we decide to fix the 3D shape initially. So we just use the average fixed image. However, we can see how we remove this restriction later. Let's take a look at some results. The UV-PCK metric gives us the quality of the surface mapping. The higher, the better. The first two rows show the performance achieved for surface mapping when using only reprojected loss instead of full ground truth supervision. And we actually see that we're able to come close to performance of dense labels, especially at higher thresholds. So now let's take a look at how we remove the fixed mesh requirements through deformed meshes. We notice that directly learning the overall shape is pretty tough. So what we realize is predicting a residual over the mean shape leads to much easier learning. So our solution involves predicting a deformation over a mean category shape and find much better results with that. We use an approach proposed earlier to model deformations at the 32 times 32 times 32 cube, which represents the exact deformation. So let's take a look at some results now. And the POSMAP PCK metric gives us the quality of the predicted 3D shape. And again, the higher the better. So here we see the benefits of using a deformation module over an unconstrained prediction. And we see that although the fixed mesh gives occasional performance, a learned mesh is able to get much better results for a finer PCK threshold. Plus, our deformed mesh module performs even better than the unconstrained. Now, let's take a look at the final piece of the puzzle, which is how do we use multiple views? How do we use that information? Notice that although we've explored right group inside a single image, we haven't utilized the full extent of our data set, the presence of multiple images. It's natural to see that multiple views of the same instance will contain more information. So let's take a look at these two images of the same face, just from different perspectives. And bring our attention to the yellow dot. Is there some pattern we see? Yes, the yellow dot is at the same location in the top-down map for both the images. And we can utilize this consistency. We propose using a multi-frame jump to exploit this consistency. Let's now see the benefits of using the multi-view consistency as opposed to using more details about how we exactly formulate this. We see modest performance improvement in surface mapping quality, and especially at a finer PCK thresholds, highlighting that utilizing multiple consistency actually helps. Now that we've covered the basics of all the components which make our model, let's take a look at our overall model performance. We see that our deformed multi-view approach performs the best. We also see a significant increase in performance when using deformation instead of a fixed mesh. And to get an estimate of how our model performs with respect to other approaches, we look at the closest comparable approach, that is canonical surface mapping by Kulkarni et al. And we observe a significant improvement in our surface mapping quality as opposed to further highlighting the benefits of that approach. We also take a look at how a fully supervised approach performs and notice that we are mostly able to close the gap, especially at higher PCK thresholds. In conclusion, we propose an approach which shows how to exploit the protection cues in a multiple setting, allowing us to effectively learn 3D structure as well as see improvements in surface mapping. We hope our data set encourages research in this direction and allows for better evaluation of comparable methods in the future due to the presence of ground truth adaptations. And that wraps up our discussion. Thank you, and let me know if you have any questions.